play the game. I make the rules. I don't play the game. I make the rules.
Time to strike! Precision and grace. Ready, Hammer? Feel the power of true ice. Ready, Hammer? definitely not the hero.
I'll sleep when they're dead.
I am the wind.
I'll sleep when they're dead.
You are definitely not the hero. Precision and grace. about to die.
Let's do this.
there's no human-made object orbiting our planet bigger than the International Space Station, or ISS for short. I think some would argue there's nothing more fascinating either. The ISS speeds through space at 5 miles per second. Imagine getting from LA to New York in less than 10 minutes. It takes about 1.5 hours to complete one orbit around our planet, and it does this a little over 15 times per day. The ISS is a real speed racer, flying about 250 miles above Earth. And don't forget, there's a whole crew of astronauts in there. The station is shared by the space agencies of the United States, Canada, Europe, Russia, and Japan, hence the whole international thing. The purpose of this joint effort is to conduct research for future space missions, such as more trips to the Moon and maybe even to Mars someday. And I'm sure it would take a whole global effort to keep this bad boy running. The estimated cost as of 2010 was $150 billion. The cost per crew member per day is $7.5 million. No wonder the station has been dubbed the priciest human-made structure in history. As of March 2019, 236 people have served aboard the ISS, and they collectively represent 18 different countries. It's had people on board continually since November 2000. The ISS usually houses crews made up of 3 to 6 individuals, and one expedition typically lasts for about 6 months before an astronaut is relieved by someone else. That's when it can get really interesting, because there might be up to 13 crew members on board at once while they're sort of changing shifts. But I imagine astronauts don't have to worry about their toes getting stepped on in a crowded place, huh? This impressive structure is often visible from Earth, even during the day, since sunlight shines on its reflective surfaces. And in case you'd like to see it, there are smartphone apps that show you when and where you can see the ISS on its next flyby over your town. Perhaps that's what helped Washington-based photographer Rainey Colacurcio snap an amazing shot of the ISS flying in front of the Sun. Just imagine, our Sun is almost 900,000 miles across. That means you could fit 109 Earth-sized objects along its diameter. So when the station crossed paths with our own bright star, it looks so tiny in comparison to that orange backdrop that's still humongous despite being almost 100 million miles away. It's an incredible picture, and it even got NASA's attention. They recently chose it as their astronomy photo of the day. They also included a statement explaining that it's not really unusual for the ISS to transit the Sun. The shocking thing is that Colacurcio was able to get her timing and equipment just right for a spectacular image. Another interesting detail is that there were no sunspots visible when she snapped the picture at that moment. That's a pretty rare occurrence, but now would be a better time than ever for there to be absolutely no spots on the Sun. You see, our star is currently in a phase called a solar minima, when you don't really see much sunspot activity. Yes, sunspots are temporary, so they come and go, sometimes lasting for months. They appear because of magnetic fields reducing the temperature on the Sun's surface. They look darker because they're cooler. Hotter areas burn bright, kind of like when you heat metal and it glows orange. These spots might look teeny tiny from here on Earth, but they can actually be as big as a planet. Still, nobody knows why there aren't any spots in the photo, even if the Sun is going through a regular phase of decreased activity. These periods, known as a solar cycle, usually last an average of 11 years. But get this, when there's a lot of activity on the Sun's surface, it can create auroras, affect electric grids, and even interfere with radio signals here on Earth. Anyway, Colacurcio's picture is actually a composite of 2 separate photos. One was of the space station crossing paths with the Sun, and the other was an image of the surface of the Sun itself. Both pictures were taken simultaneously and then sort of sewn together. And guess what? You can also take a picture of the ISS. You'll first need to set up a tripod or a mount in a place that won't experience any sort of vibrations. Set up a webcam on the mount so that it's looking through a telescope. Use an app such as ISS Transit Finder to find the station's path. You then shoot a short video magnified through the telescope. After that, use an image enhancing program to make a composite of all the frames to pull together an awesome shot that could get you some praise and respect from NASA. Or, of course, you can do it the easy way and just grab a DSLR camera or some other camera that can take long exposures. The most important thing is that the tripod or mount doesn't budge the whole time. Find the ISS and basically point and shoot when the station is passing through. So, you look at the picture and you might wonder, what's going on in that little TIE fighter-looking black speck against all that orange bubbly hotness? Glad you asked. The current ISS crew has been working on growing plants, and they plan to grow some Espanola chili peppers this November. Because, posing for an epic picture in front of the sun wasn't hot enough as is. Jokes aside, NASA is looking for something hardy that doesn't grow too tall. Now, this is a big undertaking because it'll be their first fruit grown entirely in space. Growing food is essential for astronauts on long-term missions, and fruits are perfect, especially these chilies, since they're packed with health-boosting vitamin C. Space gardens will be a major step up from the vacuum-packed food we've come to associate with an astronaut's typical diet. Plus, it's just downright necessary to grow from scratch when you're on a major time-consuming mission, like building a lunar station or colonizing Mars. A space garden would also be a way to produce oxygen, recycle compostable waste, and maybe make space residents feel a little more at home. In 2015, astronaut Scott Kelly and others made history by growing zinnias as part of a gardening program. They used a contraption called Veggie, which pretty much serves as a little onboard greenhouse for plant cultivation in space. Veggie is bringing to light the effects of low gravity and radiation on plants. It also helps astronauts determine how much water the plants need and how to manage things like mold. The crew has to monitor the lighting and moisture levels really carefully. I mean, it's hard enough keeping a houseplant alive, so just imagine how precise they need to be in a space station with no direct sunlight or even gravity. Seeds are first planted in Kevlar pouches coated in Teflon. These pouches, or plant pillows as they're called, contain soil, fertilizer, water wicks, and of course the seeds. Veggie works together with the Advanced Plant Habitat, a smaller automated lab that has more than 180 sensors and automatic watering. So yeah, ISS astronauts are up there trying to create a viable food source for us in the future once we start colonizing other celestial bodies. Currently, there are plans for the ISS to be operational through 2024, and maybe even to 2028. But after that, there's nothing on the agenda yet. It may be recycled and used for future projects such as other space stations. Until then, we can all just applaud the important work they're doing and snap a cool picture when we see the right opportunity. So how about you? Would you like to visit the International Space Station? Let me know in the comments below. If you learned something new today, then give this video a like and share it with a friend. But hey, don't go starting your own space garden just yet. We have over 2,000 cool videos for you to check out. Just click this left or right video and enjoy. Stay on the bright side of life.
The world is a big place filled with wonders, but even Earth pales in comparison to what space has to offer. And the best part is, we've barely scratched the surface. Every single year, researchers discover a lot of awesome things about the universe. Coming up are some of the most mind-boggling recent discoveries made in space. Number 15, Zombie Star. In November 2017, there was a study published in Nature about a star explosion, which is formerly known as a supernova. Not all stars explode when they die, but those with a mass 8 times bigger than the Sun do so. So what's so special about this supernova? Usually, a supernova reaches its peak brightness, then fades in a span of about 100 days. But the IPTF-14HLS supernova has been around for at least 2 years, and instead of gradually fading, it got brighter around 200 and 400 days in. again, and way back in 1954, researchers spotted a supernova in the same area. If it turns out to be the same supernova, then this zombie star has been exploding for more than 60 years, and maybe over 30 times the mass of Earth's sun. If that's the case, then this star could have condensed into a rapidly spinning neutron star called a magnetar. Another scenario is the exploding star has a mass 100 times more than the Earth's suns, meaning that stars of this size still form today, proving that not all of them have reached their complete form in the earliest stages of the universe. Number 14, underground lake in Mars. Using rock samples, scientists have found out that water does exist on Mars, but only in the form of ice and water vapor. However, there was little evidence suggesting it existed in the present time. That changed in August 2018 when a study in Science came out. It supported the notion that liquid water does still exist on Mars. The researchers used a radar called MARSIS to check what's underneath 1.6 kilometers of ice in the red planet's southern polar region, Planum Australe. Here, they detected what seems to be an underground lake 20 kilometers wide. If it turns out to be real, it will make Mars a more viable place for life to exist, and that includes human life. Number 13, far out. In December 2018, scientists discovered the dwarf planet 2018 BG18. It's the farthest known body in the solar system, hence its nickname Far Out. Second, it's the only object in the solar system orbiting at more than 100 times the distance from the Earth to the Sun. In other words, Far Out takes more than 1,000 years to make a single orbit around the Sun. But there's one more exciting thing about Far Out. You see, this dwarf planet was found where other extremely distant objects in the solar system are, and these objects had similar orbits. If researchers confirm that Far Out orbits the same way, it may help prove that there is something out there that guides their orbits, a massive planet known as Planet 9 or Planet X. Number 12, the First Exo Moon. Any natural space object that orbits a bigger astronomical body is a natural satellite. The Earth's moon, for example, is a satellite. But if the moon is orbiting a planet outside our solar system, it's an exomoon. In October 2018, Alex Teaching and David M. Kipping published a study in Science Advances about the first exomoon discovery. It was orbiting planet Kepler 1625b. That's located 8,000 light years away, which is equal to about 9.46 trillion kilometers multiplied by 8,000. If the science community confirms that this is the first exomoon ever discovered, it would help us know more about the properties of planetary systems other than our own. Number 11, nuclear pasta. In the 121st volume of Physical Review Letters published in September 2018, a study reported that the strongest known material in the universe may be nuclear pasta. Astrophysicists believe that these exist inside neutron stars, which are very dense balls of neutrons usually resulting from the explosive deaths of stars much bigger than our sun. Using computer simulations and what science knows about neutron star properties, the researchers determined the strength of nuclear pasta. The result? You'd need strength 10 billion times the force needed to destroy steel to shatter a single plate of nuclear pasta. If it does exist, it will allow astrophysicists to test their theories and models on neutron stars, including just how big a structure can be on a neutron star before it causes the crust to break apart. Number 10, Trappist 1e. In November 2018, a study published in the Astrophysical Journal noted how one of the planets orbiting the Trappist-1 star may be capable of supporting life on Earth. Located 39 light-years, or 368.94 trillion kilometers away from Earth, Trappist-1 is smaller than the Earth's sun in both mass and radius. But what's most interesting is that it has 7 rocky planets that are more or less the size of Earth. One of them, Trappist 1e, may actually have liquid water on its surface and a lot of oxygen. Researchers can better understand the evolution of planets through studying the Trappist-1 system, which could then help them identify the processes that make a planet suitable for Earth-like life to exist. Number 9, dust moons. On January 2019, 2 studies about dust moons appeared in the monthly notices of Royal Astronomical Society. To understand these dust moons, it's important to know about the Lagrange points. These are the 5 points in deep space that balance gravitational pull between the Earth and its moon. 2 of these points are L4 and L5. If a space object resides in any of these 2 points, they won't lose their position. They more or less remain about 384,000 kilometers away from the Earth and the Moon as the gravitational forces are stable. Well, way back in 1961, Polish astronomer Kazimierz Kordylewski argued that there were two clouds of dust at the Earth and Moon's L5 point, orbiting the Earth just like the Moon does. However, the existence of this pair of dust moons, now known as the Kordylewski dust cloud, proved to be controversial. But thanks to advancements in computer models and telescopes, researchers were finally able to spot the dust clouds. The findings shed light on space objects that were no more distant than the Moon, yet went undetected for half a century. Number 8. The Sun's Nemesis. Some scientists believe that nearly all stars are born with companions. For many decades, researchers believed that the Sun and its twin caused disasters on Earth. As the two pulled at each other, some comets may have gone out of orbit and were sent crashing down on Earth. This would have then resulted in mass extinctions, which is why scientists nicknamed the twin Nemesis. But according to a study in the monthly notices of Royal Astronomical Society, published in August 2017, Nemesis may not be as bad as people thought it was. Rather, it just separated from the Sun billions of years ago before melting in the Milky Way. This study changes how we see the birth of stars like our Sun, that most, if not all of them, aren't created alone, and that the companion stars aren't necessarily bad for nearby space objects. Number 7. Frozen water on the Moon. Previous analyses of the Moon gave clues as to whether it had ice or not, but this is the first time scientists had direct evidence of frozen water on the satellite. The researchers, who had their study published in the Proceedings of the National Academy of Sciences in August 2018, used an instrument known as the Moon Mineralogy Mapper, or M3, to distinguish frozen water from other forms of ice or water. They found very old ice at the North and South Poles, specifically in the cold surface craters that never received direct sunlight. If scientists could figure out a way to turn the ice into rocket fuel, the Moon could be an ideal source for space travel. Number 6. Comet giving away alcohol. In October 2015, a study published in Science Advances detailed how the comet Lovejoy released ethyl alcohol into space. Researchers observed the comet using a radio telescope at Pico Veleta, Spain. What they found was that the amount Lovejoy let loose per second at one point was equal to 500 bottles of wine. Moreover, the comet released 20 other organic molecules, which may help prove that comet impacts on Earth helped provide the molecules that would enable ancient life to flourish. Number 5. Largest ring in the solar system. In October 2009, a study published in Nature identified the largest ring in the solar system. Using NASA's Spitzer Space Telescope, researchers spotted the ring around Saturn. It was 2.4 million kilometers thick with a span of at least 128 times the radius of Saturn, which is 58,232 kilometers. Researchers believe that the ring gets its debris from the impact between Saturn's moon Phoebe and unpredictable space rocks. The debris could then explain why Saturn's moon Iapetus has two tones, that the dark side may be due to all the materials from the ring. Number 4. Closest Earth-like planet. A study published in Astronomy and Astrophysics in November 2017 detailed a special planet outside our solar system. The researchers discovered it using the HARPS planet-finding spectrograph in Chile. It's called Ross 128b, and it may have the conditions to support Earth-like life. Ross 128b is just 35% bigger than Earth, only receives 38% more sunlight, and orbits a quiet star that doesn't let out deadly solar flares. It's 11 light-years away, but it's a relatively close planet to keep an eye on, especially if scientists could confirm whether it has liquid water or not. Number 3. Oumuamua. In October 2017, researchers discovered a very unusual space object moving at almost 92,000 kilometers per hour. It was eventually called Oumuamua, and it's the first and only observed interstellar object that's passed through our solar system. Researchers know it's between 400 and 800 meters long, with a thin cigar-shaped profile, but what it is exactly is up for debate. Most of the scientific community thinks it's a comet. Others say it's an asteroid, a zombie comet, or even a spacecraft from another civilization. Some even see it as proof of panspermia, that Earth began thanks to microscopic life forms traveling in space on these space objects. Number 2. Space origins of gold. In October 2017, astronomers discovered where heavy elements such as gold, platinum, and uranium came from. With the help of LIGO and the Virgo interferometer, they were able to locate two neutron stars colliding against each other 130 million light-years away from the Earth. Due to how dense these stars are, their collisions caused gravitational waves and led to the formation of heavy elements. Researchers once thought that most of the heavy elements on Earth were due to supernovas. This discovery suggests otherwise. Number 1. First ever black hole image. Arguably, the biggest space discovery in recent years happened last April 10th with the help of more than 200 scientists. It was the culmination of the Event Horizon Telescope project, which used 5 petabytes of data from telescopes around the world. That's equal to 5,000 terabytes. It took 2 years, but the EHT finally managed to create the very first image of a supermassive black hole. Technically, what you're seeing isn't the black hole itself. You can't see it because it consumes everything: stars, planets, and even light. What you see is its silhouette, and the bright ring is the event horizon. It's the visual evidence that black holes exist. Once an object passes through here, it can no longer come back. So why is this image important? It's the only direct evidence scientists have of black holes so far. Second, the event horizon can help researchers test Albert Einstein's theory of general relativity. His theory predicted that objects the size of black holes would be spherical in form, with a ring of light surrounding a dark center. There is a ring of light, but it's coming from all directions, because the black hole is warping space and time. And lastly, it could help scientists learn the very nature of black holes. From twin stars to dust moons and black holes, I hope you learned a lot from this video. Which one was your favorite? Are there other discoveries you want to add? Let me know in the comments below. And don't forget to give a like and subscribe for more amazing content. Thanks for watching.
The universe is a very strange place by its very nature. Mysterious questions abound over dark matter, dark energy, how it all came to be, and so on. But at the same time, as our astronomical instrumentation has improved, in modern times we have been able to study the universe in unprecedented detail. As that process has unfolded, the universe has rewarded us with both understanding, but also new mysteries, many of which have not been solved. In the course of making this channel, I have run across and covered many such astronomical mysteries, some of them now solved, some of them not, but there has always been a core group that offer possibilities so weird that they continue to baffle scientists to this day. So here are 10 unsettling astronomical incidents and phenomena. Number 10. The nature of pulsars. When pulsars were first discovered in the 1960s, the possibility that they were alien beacons had to be seriously considered, after it was shown that they were not a product of Earth interference. They were, after all, highly unnatural-looking pulses of electromagnetic radiation that repeated with such regularity that some of them rivaled the accuracy of atomic clocks. In the years since, we have learned that they are just an unusual case of nature emitting a regular signal by way of a rapidly rotating neutron star. This would seemingly lay the idea of alien involvement with pulsars to rest, except it actually doesn't. In 2017, Clement Vidal authored a paper that reopened the question of an alien technological origin for pulsars, or at least a certain class of them, that could have been natural objects tweaked by aliens for communications. He pointed out that there were 5 reasons that aliens were originally taken off the table as an explanation. The first was the truly titanic amounts of energy involved. It seemed unlikely to some that a civilization would use that kind of energy. Trouble is, we've never seen an alien civilization, and we really have no idea what they would be capable of energy-wise, and we do still talk about galaxy-spanning Kardashev Type 3 civilizations that would command far more energy than a pulsar. The other 4 reasons are equally problematic. One was that they are not unique. In other words, how likely would it be that 2 separate civilizations would broadcast the same way at similar frequencies? Well, our Earth civilizations do that, and SETI does spend a lot of time looking for aliens at the frequency of 1420 MHz because there are inherent scientific advantages to do so that alien scientists would also know about. Perhaps that could be the case with pulsars. Another reason was that pulsars generally do not emanate from planetary systems, but who says aliens have to stick to a planet? Also, they are not narrowband. Kicking out broadband transmissions wastes energy, and technology generally sticks to narrowband as a result. But if pulsars started out as natural objects that are being tweaked for communications by exocivilizations, then broadband may just be a natural leftover artifact. But the 5th argument is the most solid. We have perfectly good natural explanations for pulsars that fit the bill. There really isn't a reason or need to evoke aliens when something appears explained and natural. But that doesn't eliminate the pesky possibility that pulsars could be tweaked by an exocivilization as a natural carrier for communications. And that, maybe, We should look for that, especially in light that some of them are extremely accurate in their pulses to the point that they could be used for something like a navigational beacon. That near absolute regularity present in some pulsars does look a bit odd, decades after they were first detected. Number 9. Fast radio bursts. This particular phenomenon is a relatively new one, having only been discovered in 2007. They come as very quick bursts of radio waves that arrive in such a way that scientists know that while extremely powerful, they must come from very small sources that are likely outside our galaxy, limiting what could be causing them. Further limiting what they might be is that at least one has been seen to repeat, seemingly ruling out any sort of cataclysmic event, such as a black hole merger. Most hypotheses currently on the table involve neutron stars, or magnetars, in some sort of odd situation, but it's also hypothetically possible that they could be of alien origin. In 2017, Manosby Lingham and Abraham Loeb released a paper, linked below, explaining that it's possible that the origin of at least some of them could be leakage from alien light sails, because the frequencies at which FRBs are detected happen to also be optimum frequencies for use with light sails. More, given that FRBs have been shown to originate from very small sources, they point out that the emitter for a light sail would need to be about twice the diameter of Earth, well within the constraints on what could be producing FRBs. Number 8. The Dyson Sphere candidates. Sometimes ideas within the realm of futurism can be so speculative that, if realized, are probably going to prove impractical. One such concept is the Dyson Sphere, though it should more accurately be called a Stapledon Sphere, after the sci-fi author that envisioned them in the 1930s, as opposed to Dyson's actual vision of a swarm of energy collectors. To actually encase a star within a solid shell would be a megastructure undertaking of truly titanic proportions that would involve things like completely disassembling planets for raw materials. And it's not entirely clear how such a thing would be engineered, constructed, and maintained. Surprisingly, however, out of all the hypothetical alien megastructures that we have yet envisioned, the Dyson Sphere remains the only one for which we have detected candidates, but they probably aren't very good ones and are likely really due to natural phenomena. The detections stem from a search of infrared data from the IRAS satellite done by scientists at Fermilab. The idea is that Dyson spheres absorbing energy from their star would re-emit that energy in the infrared in a specific, detectable way. They found 17 candidates that fit, though they were very ambiguous and probably have natural explanations, though efforts to figure out what they are ongoing. And another project to search for them using the Gaia spacecraft has already yielded a further 2 eyebrow raisers, TYC 7169-1532-1 and TYC 6111-1162-1, though again, they are really ambiguous. Nothing definitive, but in coming years, if civilizations do indeed encase their stars in Dyson spheres, it seems likely we'll spot it. Number 7. The Phantom Planet. Unlike most of the phenomena on this list, this one could well be explained within the next few years, as several groups of scientists are actively looking for it. The motion of objects in the outer solar system is peculiar, as though they were disturbed by a large object lurking out in the outer solar system. In fact, yet another object showing orbital peculiarities consistent with this was found recently, bolstering the case that another planet exists in this solar system much further out than the orbit of Neptune. One possibility is that it's this solar system's missing super-Earth. Our solar system is unusual because we lack a super-Earth, seemingly one of the more common types of planets in the Milky Way. This hypothetical planet may have formed closer into the solar system, but might have been pushed out early in the solar system's history. Another possibility is that it may not be from this solar system at all, and may be a captured object the Sun acquired at some point in its history, in which case it would be a truly alien interloper in our solar system, and would offer us a chance at studying an actual former exoplanet that formed somewhere else. While it's not universally accepted that Planet 9 must be out there, there is also an argument that the data is skewed and it may not exist at all. Whatever the case, as hints of this phantom planet's existence continue to surface, it seems very possible that within a few years we may well have another known planet to explore. Number 6. TYC 8241-2652. This entry is truly bizarre because not only is there no ready explanation for it having happened, but also there's no ready explanation for how fast it happened. In 1983, the star TYC 8241-2652 was observed in the infrared to have a debris disk. That in itself is nothing unusual. Dust disks are a normal part of planetary formation, and indeed Earth itself formed from one. And over time, a very long time in geologic terms, these disks tend to clear out as stable planetary systems develop. When TYC 8241-2652 was observed in 2010, the dust disk had completely disappeared, not in millions of years, but in the time since a previous observation in 2008. Whatever caused the dust disappearance did it in under 2 years. Numerous natural explanations were suggested for just how that could happen, only to fall flat, and the cause for the disappearance remains a mystery, and has been seen in no other star system with debris disks since. Number 5. 234 detections of something strange. Occasionally, a scientific paper will come out that's seemingly worthy of attention and then instantly goes into obscurity. That's essentially what happened with a paper by Ermanno Bora and E. Trottier in 2016. It related to an earlier paper by Bora, where he predicted that certain types of pulses could be produced by current technology and be detected 1,000 light years away, and vice versa. Bora then searched existing data for anything that might look like those kinds of signals. He found 234 of them. Now, the media at the time sensationalized the story, and in some cases badly reported it, as though aliens had been found. This was not the case, and the scientists themselves made no claims that this was an actual detection of alien civilizations, merely that that was a possibility and that further follow-up work should be done. And that's where it sits today. But one thing still stands out. Nearly all of the detections were coming from stars of spectral types believed to be suitable for life. Number 4. The WOW signal. This bizarre signal in some ways gets even more bizarre as time goes on, simply because an alien origin for it cannot be ruled out, even though the signal was detected over 4 decades ago. In 1977, astronomer Jerry Amon, using the Big Ear radio telescope at The Ohio State University, picked up a signal. This signal was noteworthy for several reasons. The first is that it was very close to 1420 MHz, which is the frequency at which hydrogen, the most common element in the universe, emits radio waves. This frequency is of note to SETI scientists. In fact, it's set aside and not broadcasted on specifically for this reason, because any alien civilization that possesses science and radio transmitters would know of this frequency. As a result, it might be a universal frequency to broadcast a contact signal. The second is that the WOW signal was strong, very strong, which is why Dr. Amon famously wrote WOW on the printout. The third strange thing about the signal was that it was narrowband. Nature tends to emit radio signals broadband, whereas technology tends towards narrowband. Another odd aspect of the WOW signal is the fact that it was a very brief signal, in that it was there, then it was not. That seems counterintuitive for a contact signal, and it's never been picked up since, despite plenty of attempts to do so. Perhaps the strangest aspect of WOW, though, is that it keeps defying explanation. It's never been shown to have been Earth interference, or a glitch in the equipment that picked it up. To this day, potential explanations continue to be put on the table, only to be shot down. This happened most recently with the hypothesis that WOW might have been due to emissions originating from comets, and this was widely reported in the press as a case-closed explanation. What they didn't report as widely is that the comet hypothesis was shot down by the scientific community very quickly. If comets emitted that strongly at the hydrogen line, radio astronomers would have noticed that by now, and it should be easily observable. It's not. So to this day, the WOW signal remains unexplained. Number 3. Strange signals. While the WOW signal is the most famous of the unexplained odd radio signals SETI astronomers have picked up, it is not unique. Other examples include a signal picked up just once and did not repeat from the direction of the star TYC 1220-91-1. What's notable about the signal is that it appeared to originate from a nearby star that's very similar to our Sun, and potentially habitable. It was also at a magic frequency mathematically related to the 1420 MHz hydrogen line. It was also narrowband, and was observed for a full 10 seconds. But most noteworthy was that the signal was so strong, about 10 times stronger than WOW. But since that signal didn't repeat and couldn't be verified, it can't ever be determined if it was simply Earth interference. Other unverifiable signals include a 2015 signal from the star HD 164595, another very sun-like star, but this time with a verified planet in orbit around it, but it never repeated. And it happened to be in a military band, and it seems likely that there are satellites downlinking from orbit that scientists may not be aware of. And then there was the signal SHG-B02+14A, which was weird even for a signal plausibly of alien origin. Firstly, unlike most, this signal repeated, having initially been observed 3 different times, and it was at the 1420 MHz frequency, initially, but then it would drift. More, there didn't seem to be any corresponding star system to where the signal was coming from, and it was very weak, and if it originated on a planet, that planet would have to have been rotating 40 times faster than Earth. Number 2, KIC 8462852, Tabby Star. In 2015, a star was found in the massive amount of data collected by the Kepler spacecraft that was behaving like no other star previously seen. It would experience dips in brightness of up to 22%, suggesting that something extremely massive was passing in front of the star. Initially, it was uncertain as to what this could be. A cloud of dust wasn't a good fit because star systems that have dust disks tend to emit infrared radiation brightly. No such radiation was found at KIC 8462852. The star's main investigator, Dr. Tabitha Boyajian, suggested that it could be cold comets blocking the light. But on further investigation, it was found that the number of comets needed to produce the effect would have been implausible. More, another study found that exocomet signatures in the Kepler light curves don't fit what's going on at Tabby Star. Given that natural explanation after natural explanation were falling flat with the star, the idea that gigantic alien megastructures could be blocking the light was starting to be seriously considered. Now, even that doesn't fit, as later research showed that whatever was blocking the light, at least with the most recent dips measured from the ground here on Earth, was not opaque, and that dust and some sort of bizarre juxtaposition around the star had to be the cause. But there's still that question of the missing infrared. To date, no one knows exactly what's going on at KIC 8462852. Number 1. Seville Ski Star. At the time when the KIC 8462852 story was a media hit, it was often called the strangest star in the universe. And while it certainly was strange, this final star on our list gives it a run for its money. This star is called Seville Ski Star after the Polish-American astronomer that first studied it. The star is what's known as a peculiar star, a class of stars that are chemically unusual in some way when compared to other stars. But even then, this star stands apart because it contains elements that really shouldn't be there, and are more at home in a laboratory on Earth than they are in nature. And it's not just a handful of odd elements, it's a lot of them, in sufficient quantities to be detectable at great distance in the star's spectrum. Elements like praseodymium, ytterbium, technetium, and promethium are present, the last only discovered through the activities of the Manhattan Project. Certainly odd, but stars can have odd elements in them. But there's more. The star is also anomalously low in iron and nickel, abundant elements in the universe. But perhaps strangest of all are the very short-lived actinide elements higher on the periodic table than uranium. Quite a few of these are present, and it's just weird, but one in particular raises an eyebrow: plutonium. Plutonium is thought to be produced only in minute quantities in nature, and only under specific circumstances. For this star to have it in abundance is a complete mystery, though hypotheses have been put forth that you might be able to get to elements higher than uranium if the star were bombarded by a neutron star, or some unknown nuclear process within the stars creating elements. But it's worth mentioning that in 1966, Carl Sagan and Joseph Szostak hypothesized in their book Intelligent Life in the Universe that one way for an alien civilization to announce its presence to others would be to add large amounts of plutonium to its star. Thanks for listening. I'm futurist and science fiction author John Michael Gaudier, currently planning Halloween episodes for both channels, this one and Event Horizon, link to that channel below. Halloween is my favorite holiday, and I've been busily filling my house with dried ears of corn and various carved gourds, as is the custom here. And be sure to check out my books at your favorite online book retailer and subscribe to my channel for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.
Feel the power of true ice.
When the ancients looked into the night sky, they thought the heavens revolved around the Earth and mankind. Over the centuries, this view has changed radically. We discovered we lived on a planet orbiting a star within the solar system, and this solar system was found to be part of the Milky Way galaxy. Later, we learned that our universe was filled with billions of other such galaxies. But could it be that we're committing the same error as our ancestors by thinking the universe contains everything there is? Could it be that we live in a multiverse?
The word multiverse refers to the general idea that our universe might not be unique. There might be many, many universes. And there are a number of different ways of thinking about multiverses.
Now, this idea of a multiverse is not gratuitous speculation. No, it really comes out of both experiment or observational physics about the universe and the current theories as best we understand them.
There are a number of different theories about what the multiverse could be. One proponent of the idea of the multiverse is Max Tegmark of the Massachusetts Institute of Technology. Dr. Tegmark suggests a four-fold classification of possible types of multiverse. The first type of multiverse is just an extension of what we already know, our universe expanding into infinity rather than ending at the limits of our vision.
When we astrophysicists talk about our universe, we don't mean everything that exists. We mean this. We mean the spherical region of space from which light has had time to reach us so far. Because no matter how good telescopes we build, if there's a galaxy out here, light from it just hasn't reached us yet. We have no access to it.
We can look back almost to the beginning of time, shortly after the Big Bang, some 13.8 billion years ago, to the edge of the observable universe. But we can see no further, so the space beyond that distance, known as the Hubble radius, is literally out of sight. But that doesn't mean there isn't anything there.
We've got every reason to think that our universe goes on far beyond what we can see, that there are many galaxies which are unobservable because they're so far away. And indeed, many people think that the universe extends far, far beyond what we can see, maybe billions of times further.
Because the expansion of the universe has stretched space, astronomers are able to see out to a distance of about 42 billion light years. How far things extend beyond this is unknown, but may not be unknowable. And if they stretch to infinity, as some theories suggest, there could be numerous isolated universes, cut off from one another by their own Hubble radius, depending on the observer's vantage point.
I don't have a single colleague in science who thinks that space actually ends here at the edge of our universe. Where it starts getting more controversial is when you ask, well, how much more space is there?
To understand the second type of multiverse in Dr. Tegmark's system, it is first necessary to understand how the universe was formed and the theory of inflation. It was first conceived of by Alan Guth in 1979, and then later refined and expanded upon by Andre Linde, who had some key insights.
So inflation is a twist on the classic Big Bang theory. It's really an answer to the question of what is it that tells the Big Bang.
But initially the universe was kind of energetic vacuum-like state. The universe expanded nearly exponentially fast, and during 1 trillionth of a trillionth of a trillionth of a second, it have grown up to the size much larger than the size of the part of the universe which we are capable of seeing right now.
The thinking is that inflation may not have stopped at the same time everywhere. So we live in a universe that was spawned by one area of inflation, but bubble universes, or pocket universes, could have continued to form elsewhere.
We don't know much about how inflation started, and we don't know if it started only once or many times. Perhaps it started many times. But even if it only started once, that's enough to create an infinite number of these pocket universes, because once the inflation goes, a pocket universe forms here, a pocket universe forms there, and just goes on forever.
And as a result, the universe becomes a self-reproducing, eternally growing fractal.
What these universes could be like is a mystery, but it is conceivable that the laws of physics within them would be totally different from our own.
They may not allow gravity to exist, they may not allow a periodic table of elements, they may not allow stars to be stable for long enough, etc.
This is one of the ideas of string theory, which attempts to unify general relativity with quantum mechanics. The thinking is that all of the solutions produced by string theory that don't match up with what we can see in our own universe may actually represent reality in other universes.
So, the basic idea of the multiverse is that the different solutions of string theory control the environment in these different regions very far away.
So, if we are in a multiverse where the different constituents are governed by different physical laws, then we have to introduce a concept called anthropic selection. The idea that we are not in a typical universe, because most of them will be sterile or stillborn, because the laws governing them won't allow complexity to emerge.
The anthropic principle is the idea that our universe is fine-tuned to allow humans to live. A small fiddle with the strength of gravity, for example, and life as we know it would not exist. A coincidence that does not sit easily with scientists. The concept of a multiverse neatly addresses this problem. Within the infinite number of universes that could exist, we are simply living in the one we are able to. In the third type of Tegmark multiverse, as in the first, the laws of physics are the same from one to another. In this type, though, the component universes are separated not by distance, but by time. At every moment within such a multiverse, all of the possible futures allowed by the uncertainties of quantum mechanics actually happen.
Quantum mechanics is not a predictive theory, it's a probabilistic theory. So it says, for example, if a photon goes through a polarizer at 45 degrees to the angle of polarization, it just has a 50-50 chance of going through or not, and there's no way of knowing. One interpretation of quantum mechanics, which I think makes a lot of sense, says that when the photon hits the polarizer at 45 degrees, there's actually two futures that happen. One where it goes through the polarizer and one where it doesn't, and each future continues as if the other future were not there.
In the many worlds theory of the multiverse, the entirety of the universe acts like the quantum photon, but instead of having two potential future states, every possible outcome would be manifested. So our entire universe and everything within it, including you, would be constantly undergoing multiple fissions into daughter universes, each with its own reality and future. Any given observer, though, would only see one outcome. In the final classification, the Level 4 multiverse, Dr. Tegmark proposes that all coherent mathematical systems describe a physical reality of some sort. Those different systems are, of necessity, different universes. What this last idea translates to in practice is hard to conceive of. It is more the province of metaphysics than physics. But the other three types of multiverse, though they push the bounds of physical theory, do not overstep them. Observational data supporting the theory of inflation have convinced some scientists that a multiverse is possible, but the idea is still controversial.
I think the jury is still out on whether there's a multiverse. It's odd that some people get very emotional, some people are very hostile to the idea because they don't feel we should talk about entities that we can't directly observe. I think we've got to be open-minded because we have good theories which predict that a multiverse must exist. And I hope that we can settle this. I think it's an empirical question.
Although the idea that there are other universes, I regard as a very reasonable speculation of modern cosmology.
Taking a step back, I mean, it's proven very difficult, surprisingly hard, to come up with a theory of physics that predicts only what we see and predicts that there's nothing else.
It may be impossible to ever directly observe the multiverse, but some scientists hope to eventually gather enough data supporting the theories that predict it to one day confirm its existence. If that were to happen, like the ancients before us, we would be given a whole new perspective on how the cosmos works, and on our place in it. Is there life elsewhere in the universe? Anyone who has pondered the immensity of the cosmos has probably wondered at some time or another whether life exists beyond our planet.
One of the most interesting and exciting questions that people have been asking for millennia is, are we alone? You know, even as a child, I stared up at the night sky, saw all those stars, and couldn't imagine that some of them didn't have planets with people on them who were looking back at me, wondering the same thing. We are now at the point where we can scientifically answer that question.
The search for life beyond Earth has been buoyed by recent discoveries made by NASA's Kepler Telescope. It's looking for planets outside our solar system known as exoplanets. Kepler measures the brightness of distant stars and tracks a star's dimming when a planet passes in front. Up until 1995, exoplanets were purely theoretical, but scientists have since identified thousands of them.
You know, just 20 years ago, we didn't know of any planets beyond our solar system. And now here we are, we know that there's pretty much a planet for every star. And then we know about 1 out of every 5 of those planets could harbor life. That's such a profound difference in 1 generation's worth of work in our understanding of the cosmos. It blows me away every time I think about it. And it blows me away every time I go out at night, because I can literally go and not just count stars, I can now count planets.
But one thing that has been very important, and is one of the real growth points of astronomy at the moment, is the realization that most stars are orbited by retinues of planets, just as the Sun is orbited by the Earth and the other familiar planets, and that many of those planets are rather like the young Earth. There are probably within our Milky Way galaxy billions of planets rather like the Earth. And of course, many people would guess that there is life on them, but we can't be so sure about that, nor what life is like.
In July, NASA scientists announced the discovery of one of their most exciting exoplanets yet, Kepler 452b. Located some 14,000 light-years away, the planet is in the habitable zone, which means it's the right distance from its own sun and also the right size to potentially be Earth-like.
So Kepler 452b is one of the most habitable planets, or one of the most potentially habitable planets that we've ever found. Of the things that we're able to measure about this planet, there's a lot of it that seems much like what we experience here on our own home planet. And that's what's got a lot of the scientific community so excited.
There is a limit to how much we can learn about Kepler 452b because of its distance. NASA is launching the James Webb Telescope in 2018 to find Earth-like planets closer to home, so they can study their atmospheres for biosignatures that would indicate the presence of life. But there's another way to learn more about distant planets beyond what the Kepler Telescope can tell us, and that is to look for signs of intelligent life. Frank Drake has been listening out for signals of intelligent life elsewhere in the universe for over 50 years. Mr. Drake came up with something called the Drake equation, which is a mathematical formula that estimates how many advanced civilizations capable of transmitting signals might exist in the universe. He co-founded the Seti Institute, the search for extraterrestrial intelligence. Scientists at the Seti Institute have been searching for intelligent life for the past few decades.
How does SETI search? Well, we look at our own technology and determine which one of our technologies is detectable across the distances which separate the stars. What we can detect is our radio signals, our television broadcasts, of which of course there are thousands, our radar transmissions, which are even easier to detect. And so we search for those. And so just recently to the radio search, we have added a light search.
SETI researchers have not come across any signals yet, but they say this is to be expected.
So in our galaxy, a couple 100 billion stars. We've looked carefully at maybe a couple of thousand stars, right? That means we've looked at 1/1,000,000th of the star systems in our galaxy carefully, 1/1,000,000th. So, you know, that's like going to the ocean, taking a glass of water and saying, you see any sharks in there, Bob? Well, I don't. I guess there are no sharks in the ocean. Well, that'd be a little premature, right? All it means is your sample size isn't big enough. And that would be very discouraging if it weren't for the fact that the technology keeps getting faster. So there's hope.
SETI's efforts recently got a huge boost with the launch of Breakthrough Listen, overseen by Martin Rees, Stephen Hawking, and Frank Drake, and funded by Silicon Valley entrepreneur Yuri Milner. The project will greatly expand the organization's capacity to search and sift through data. But scientists aren't only interested in discovering life forms light years away.
Of course, the only places we can directly look for life apart from Earth are on the planets and moons of our solar system. And there has been talk about, could there be some kind of life on Mars? Could there be something on comets? Could there be something under the frozen ice on Europa, one of Jupiter's moons, or Enceladus, one of Saturn's moons? And it's possible that people will find life. No one expects any very complex life in those places, but even evidence of simple life would be important.
At first glance, our solar system seems like a rather unlikely place to find life beyond Earth. But the reason scientists think it is plausible is because of the discovery of a group of organisms called extremophiles that live on Earth.
So extremophiles are a group of organisms that we've discovered that live in what we consider extreme environments. And so we have found organisms that live at temperatures that exceed boiling water, at pHs the same, lower than battery acid.
Scientists are looking at the moons of Jupiter and Saturn, as well as our nearest neighbor, Mars.
And so what we're looking for is something that might, with a microscope, might look like life. Life needs water, so we've been very interested in water worlds. So what the Curiosity rover is doing now is going around Gale Crater and investigating ancient riverbeds and features that indicate, and chemistry that indicate that there was water present.
You know, you look at Jupiter, it's a big gas ball. You figure there'd probably no life there, and that's probably true. But Jupiter has, I don't think, like close to 70 moons that we know about. And several of them are very large, you know, the size of our own moon, maybe even a little bit bigger. At least 3 of them are thought to have underneath their surfaces, and the surface might just be ice or rock, but underneath, maybe 10 miles down, maybe 100 miles down, they might have liquid oceans, hidden, dark, inky dark oceans down there with liquid water that's been sitting there for 4 billion years. So after that length of time, there might be something that's cooked up in there.
The hope is that if we find further life in our solar system on places like Mars, we will improve our understanding of how easily it might have started elsewhere. But there is another way to answer this question, determining how it started on Earth.
So until we understand how life began, we don't know how likely it is or how unique the pathway was that led to life on Earth.
One man who is trying to come up with an answer to this question is Jack Szostak. In his lab at Harvard University, he's trying to determine how easy it is to create life by making it himself.
So we work on the origin of life. We are trying to do simple experiments in the lab that will give us some clues as to how life got started on the early Earth. Our approach is to work with the chemicals that we think were involved and try to see how they could assemble into a simple kind of cell.
Modern cells are intricate nanoscale factories stuffed with thousands of different chemicals, each taking part in a complicated and messy web of reactions. Long strands of DNA encode a cell's genetic information. Shorter strands of RNA carry that information around the cell, telling it how to manufacture the proteins that run the chemical reactions it requires to live. It seems unlikely that these systems all evolved at the same time. At the Szostak lab, they're focused on 2 experiments. One to work out how primitive cell membranes could grow and divide into daughter cells, and the other on RNA replication.
So we hope to be able to recreate the conditions in lab that allowed life to come about in the first place on the early Earth. And a big part of that is learning how to make RNA that can undergo spontaneous self-replication without the need for modern-day enzymes.
Dr. Szostak and his team have already created a protocell from a blob of lipids which contains RNA. The sticking point at the moment is working out how to make RNA that can copy itself without relying on a helping hand from RNA enzymes.
The ultimate goal of this is to create, from chemicals, a simple living system where we can see Darwinian evolution operating, the emergence of new functions. So in a sense, it would be a reconstitution of the beginnings of biology in a lab setting. One of the things we hope to learn from that, of course, is how life might have started on the early Earth.
If it is a difficult process, reliant upon various bits of luck or circumstance, then it is possible that we are a cosmic fluke, one that isn't going to be repeated elsewhere. But if experiments like Dr. Szostak's show that life emerges easily, then the odds of life appearing elsewhere in the universe look more likely. Perhaps one day, when we're looking into the night sky, we'll finally know the answer to the question, are we alone?
What's at the edge of the universe? And what happens if we try to get there? You might be thinking, wait, how is there an edge to the universe if it's infinite? This gets talked about a lot, and people usually say one of the following. The universe defines all of space and time that exists. Well, that's one definition of universe, but is it even part of our universe if we can never interact with it? And what if our universe is very, very different beyond the edge? The universe is infinite because general relativity tells us that the universe is demonstrably flat, and therefore the galaxies go on forever. But how flat? Are you sure you measured the universe's curvature with infinite precision? And my favorite, we can never know and never test it, so it's not even a scientific question. Oh yeah? I'll science any question I please. This is space-time. Okay, sorry. Before we get carried away, let's talk about the edge or edges of the universe and what it might take to get there. In a previous episode, we talked about the size of what we call the observable universe. We even gave you a number, 93 billion light years in diameter, 46 billion in radius. Go ahead and watch it again. It'll be useful. While you're at it, we're also going to be talking about the CMB, so it wouldn't kill you to watch that episode also. Okay, let's start with that 46 billion light year number. We defined that as the current radius of the known universe. It's the distance to that blob of the CMB, the most distant thing we can see in that direction. Now, it's not 46 billion light years to that actual blob. It is currently 46 billion light years to whatever galaxy or galaxy clusters that blob evolved into, racing away from us with the expanding universe as it did. We call this the particle horizon of the universe. It's the current instantaneous distance to the most distant part of the universe that could possibly have a causal connection to us. Anything inside the particle horizon is referred to as the known universe. Now, when I say the current instantaneous distance, I mean it's the distance that you would have to travel only if the universe froze in its expansion and you were traveling through static space. In cosmology, this sort of instantaneous distance is basically what we call the proper distance between 2 points. But nothing actually ever travels the proper distance. That's not how space-time works. The shortest path in space-time is defined by the geodesic, the path of light between 2 points. Even light takes time to make any journey, so we have to factor in the time interval, especially when space is changing. To travel to the particle horizon, we need to move through expanding space. And the closer we get to our destination, the more space will have expanded over the remaining distance. How far would you have to travel? Bad news, you'd have to travel infinitely far, even if you were in a spaceship that could travel at the speed of light. Just as black holes have event horizons, so too do universes. The event horizon of a black hole is that point beyond which we can never receive information because light from that point is redshifted into oblivion. It's a boundary to the observable universe. There's a region of this universe from which we can never receive any new signal. That is, any signal that's emitted today. This is because the distance that signal has to travel to get to us will be expanding faster than the speed of light before the signal reaches us. Same thing applies to our light speed spaceship. We can never get to anything beyond the cosmic event horizon because that space will be moving away from us faster than light before we reach it. Now here's where it gets weird. The event horizon of the universe is actually closer to us than the particle horizon. Given our best measurements of cosmological parameters, we think that the cosmic event horizon is around 16 billion light years away. This means that there are galaxies that we can see now that we could never reach or even communicate with. We're sort of seeing ghost images from outside the part of the universe that we could ever interact with. As our universe expands, more and more of it will cross the event horizon, and eventually almost all of it will be lost to it forever. Kind of sad, really. Of course, all bets are off if we can break the cosmic speed limit, so let's do just that. There's no doubt that Einstein was right in setting that limit for objects moving through space, but two regions of space can have superluminal relative speeds. That's actually the motivation behind the warp drive, which we might get to in a later episode if you're up for the challenge. But for now, let's just assume we have a nice Alcubierre class warp ship and we burn the mass energy of entire stars to chase the particle horizon. What do we find? Almost certainly, just more universe. Bummer. Remember, the particle horizon is just defined by the limit of our current view. Move to my left and my observable universe moves with me. Wait a minute, and my particle horizon expands. Travel to the particle horizon instantaneously, and you'll see the Milky Way as a cute baby CMB blob on your new particle horizon, and presumably a pretty similar distribution of galaxies and clusters all around you. But what if we keep going? What's far beyond that edge? Well, that all depends on the geometry of the universe. On the largest scales, the geometry of space-time is very flat. It's lumpy on small scales due to stars and galaxies, but smooth on large, sort of like ripples on the ocean. Measurement of the distribution of galaxies and the CMB confirm this flatness with very high, but not infinite, precision. If space-time really is perfectly flat, then with the most simplistic application of Einstein's equations, we get that the universe is infinite. Now, people claim this a lot. So, if it's true, what happens if you cross the particle horizon? The universe just goes on and 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 on, and infinity is its own amazing beast, and there are many types of infinity, including some that involve infinitely repeating versions of this bit of the universe. But is our universe really perfectly flat? Think about it this way. The surface of the Earth looks pretty flat to us because we really can't see the curvature locally. But get some perspective by taking a ride on the International Space Station, and it's clearly curved. What if the curvature of the universe is so small that we're just not seeing far enough or measuring precisely enough to detect it? It's very possible that the universe has curvature just inside the uncertainty range of the best measurements to date. If that curvature is positive, then it may be that the universe is really the surface of a hypersphere, the 3D surface of a 4D sphere. In that case, our warp ship would eventually travel all the way around this curved hypersphere and get back to where it started. Okay, so how far would it have to travel? Based on a recent estimate of the minimum radius of curvature of the universe, you'd need to travel an absolute minimum of 18 times the distance to the particle horizon to get back to where you started, assuming expansion froze for the whole journey. We also have to keep in mind that these geometries assume that we can just extrapolate Einstein's equations in the most simplistic way. In addition, although general relativity is pretty cool, it's not a theory of everything. Non-crazy ideas for the origin of cosmic inflation suggest that our universe may just be a slowly expanding bubble in an exponentially, infinitely inflating multiverse. Now, bubble universes may be finite in size, regardless of internal geometry, and so they may have a true edge. But what's on the other side? Are the laws of physics or even the number of dimensions the same? Tell us what you think in the comments. We'll cross that edge into the multiverse in another episode of Spacetime. Squishina and others ask whether it's contradictory or circular to use Einstein's theory of general relativity to prove itself. Well, the only way to test a theory is to use it. However, you're right in thinking that just one prediction is not enough. A model has to make multiple independent and accurate predictions to be accepted as a theory. And there are few theories with as many independent and accurate predictions as general relativity. For example, the predictions GR makes for planetary orbits can give us a mass for the Sun. And that mass predicts the deflection angle for light passing the Sun perfectly, that is, its gravitational lensing effect. Same with galaxy clusters. The galaxy orbits give us a mass for the dark matter in the clusters, and the lensing gives us a mass consistent with this. ShadowMax889 asks why stars and planets aren't filled with dark matter. Now this is a great point. Dark matter is cold and clumpy, which means it can bunch together to form galaxies, but it doesn't interact with itself in any other way besides gravitation. This means there's a limit to its clumpiness. To collapse completely into a star-sized object, it would have to lose a lot more energy. This is really hard unless you can interact electromagnetically. By comparison, the cold hydrogen gas that fills our galaxy clumps together in giant clouds, but then these clouds radiate light in different ways, allowing the gas to cool even more and collapse into stars. Dark matter doesn't do that, so it stays sort of puffed up. Mr. Lewis asks if we can please stop throwing monkeys into black holes. Don't worry, no monkeys were harmed in the making of space-time in any events that could be consistently assigned to our clocks at PBS. Isvazone informs us that upon winning a Nobel Prize for discovering dark matter particles, he or she would spend all of the prize money on Phoenix cases. And yeah, I guess that's cool, but I only play 1.6.